crossed into the magnetic field. External magnetic field that the current loop is positioned. Where the magnetic dipole moment is obtained by multiplying the current in the loop by the area vector. And the area vector is taken perpendicular to the plane of the loop. Okay? So for example, if you look at this particular loop here in this picture, the area vector is perpendicular to the plane of the loop. So the loop is like this, for example. But notice that the current is this way. So perpendicular to the plane of the loop would be either that way or this way. So how do you choose this from this or this from that? So you curl your 4 fingers of your right hand in the direction of the current around the loop, and then your thumb selects the direction of the area vector that's perpendicular to the plane of the loop. Yes? So, just, it will be in the direction of the thumb. So, what you need to know is that the area vector is perpendicular to the plane of the loop, right? And if you look at this expression over here, right, this current is just a scalar quantity, right? So, if you look at this expression from the mathematics point of view, then this is a scalar quantity which is positive, so many amps, 3 amps, 5 amps, 7 amps, 30 amps, whatever that is, 2 milliamps, whatever that is. And so this vector here has to point in the same direction as the area vector. So if you see the arrow indicating the direction of the magnetic dipole moment vector, it's in the same direction as the direction of the area vector. And once you calculate that for a particular loop, then you take the cross product of that vector with the external magnetic field that loop with current I in it has been placed in. So this is an external magnetic field, right? That has nothing to do with the loop. The loop has a current in it, and it's been placed in some region where there already exists a magnetic field. The question is, what will this external magnetic field do to the loop? And what will happen is that it will exert forces on the different segments, different parts of the loop, and it could cause the loop to spin, to rotate. And if it would cause it to rotate, then there is a torque. And using this formula is how you calculate the torque that would be acting on the loop exerted by this external magnetic field. So if you want to, you can write this, just take that expression and plug it in here. This would be written like this. And from this expression, this is a scalar quantity. So notice that the direction of the torque vector will be in the direction of the cross product of the area vector of the loop with the external magnetic field.
Just to be sure, the area vector is from the right hand, the direction is from the right hand rule?
So it's perpendicular to the plane of the loop. So if I have a loop like this, the area vector is either this way or that way. If the loop is like this, the area vector is either up or down. And if the loop is like this, it's either towards you or towards me. The question is, which of the 2 possible directions do you select? Then you have to look at the direction of the current around it. And if the current is this way, then use your right hand, curl your fingers in the direction of the current, and then that's the direction of the area vector. But if the current happens to be the other way, you curl your fingers in that rotational sense, and then the area vector that you would select would be the other perpendicular direction. So it's always perpendicular to the plane of that loop. The question is, well, you have 2 choices. Then you would have to have a current around the loop. If there is no current around the loop, then it could be either one. Then you select whichever one. But if there is no current around the loop, there wouldn't be a torque. Because there wouldn't be any forces on the individual pieces that make up the loop. Yes?
This has nothing to do with the magnetic field created by the loop.
Right. This is an external magnetic field. If, the fact that there is a current in this loop, that leads to the generation of a magnetic field generated by the loop. But that's not the magnetic field that we're talking about over here. Right? We did problems in chapter 28 where, if here's a current in this, in fact, in your test there was a question, right? Here's a current in this coaxial cable or whatever that was. What's the magnetic field inside? What's the magnetic field outside? There was a problem, I think, I don't remember. Yeah, there was a problem with a ring. And the question like this, for example, that now there is a current around the ring, and what is the magnetic field right at the center? Derive that expression. So it's a different question, right? There is this, what we're talking about is there is a magnetic field generated by some charges moving somewhere. Let's say the magnetic field in this room is to the right. And then the magnetic field is there, it's, generated by some moving charges somewhere. And then I take this loop with current in it and I place it in this magnetic field generated by whatever those other charges are that are moving. What will that external, so that magnetic field is external to the loop. What will it do to the loop? And it could exert a torque, given by this expression. Yes. So, the loop itself may have just one turn. What would happen if the loop has two turns? Like 1, 2. Then one of the turns has a magnetic dipole moment. Let's say suppose the current is this way. So then one of the turns creates has an area vector this way, right? With the magnetic dipole moment vector pointing that way. And the other turn has, it also has the current that way. So it would also have a magnetic dipole moment vector pointing this way. How do you find the sum of two vectors that point in the same direction? You just this plus this, right? And what if you have a third turn? So it would be the magnetic dipole moment of one turn times 3, because you got 3 turns. What if you have 10 turns? Then each turn has a mu, 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 so it's mu times 10. So, sometimes what you consider is a coil. So you can have a coil with, you can say 1 turn. Well, I guess you can just call that a loop. Or many turns, like n turns, for example. If it's just 1 turn, I tend to call it a loop, a current loop. But if it has many turns, then one tends to call it a coil with a coil. It's a coil. It's the difference between a coil and a loop. In that case, you could say that the magnetic dipole moment of the coil with capital N turns will be, that's the magnetic dipole moment of 1 turn, and then you just multiply by the number of turns. Because you're going to have all of those vectors pointing in the same direction. And if you plug that in here, then you pick up another factor of n over here. So I guess if you have a coil or a loop with only 1 turn, then capital N is 1, and you just make that n equals to 1, and you just have IA cross B. So this is a more general expression if you're considering a coil with many turns. So let's consider a specific example. I don't remember how I tend to just make up these examples And, but what if you have, let's just cook our own example here. What if we have a coil with 5 turns, okay? How about if this is a rectangular coil with 5 turns? And I'm gonna draw the coil like this, okay? And the current in it, I'll let you choose. What direction would you like the current to be? Clockwise or counterclockwise? Clockwise? All right, so clockwise it is. So I'm going to choose this current clockwise. And I'm going to pick a number here different from 5. So this is N. I'm going to make this 2 amps. I'm going to make this length over here 4 meters. And I'm going to make this length over here 3 meters. It's a rectangle, so, you know, this one is also 3 meters, but the current is this way. Now, suppose this rectangular coil with 5 turns, that would be like, you know, that's 1 and then 2, 3, 4, 5. 5 turns, right? Let's place this coil with 5 turns in some magnetic field generated by something else. What direction would you like that magnetic field to be? Would you like it to be to the right, to the left, up the board, down the board, not into an outlet, just say right, left, up, or down the board?
Up.
Up, I heard up first. So up it is. And let's make that external magnetic field. Let's see, I got a 3, a 4, and a 2, and a 5 over there. I'll make it 6 Teslas. So this is a uniform external magnetic field. Uniform is the same everywhere in this region of space over here. Up, up, up. Okay? That's B external. So question, how will this coil spin, turn, rotate as a result of being placed in this external magnetic field? Let's calculate the torque that this external magnetic field exerts on this coil with current in it. So, question. What is the torque exerted by the external magnetic field on the coil? So what is that torque? Well, the torque will be mu cross B. Okay? Mu for the coil. And that's B external. So, but what is the magnetic dipole moment of the coil? So, mu for the coil is going to be the number of turns times the magnetic dipole moment of just 1 turn. So it'll be mu, and I'll just say 1 turn. But what is the magnetic dipole moment of just 1 of the turns? So mu of just 1 turn will be the current times the area vector. So, what is the current in the coil? 2 amps, correct? And what is the area vector? In fact, let me write down the units, 2 amps. And what is the area vector for that 1 turn?
12 meters squared into the page.
So it would be 3 times 4, which is 12 meters squared, right? And what will be the direction of that area vector?
Straight into the board.
Into the board, correct? So the current is, the coil is vertical. So the perpendicular to this coil is either out of the board or into the board, but since the current is in the clockwise sense direction around the coil, I'll just curl my 4 fingers of my right hand and my thumb points into the board. Right? So this is into the board. So the magnetic dipole moment of just one turn I tend to write this as mu, like, just do one turn like that, something like that, is 2 times 12 is going to be 24 amps times meter squared, right, into the board. So I'm going to take that and I'm going to put it in here. This is the coil, right? Coil. So that the magnetic dipole moment of the coil, the whole coil, right, is I have 5 turns, and the magnetic dipole moment of just one of those turns is 24 amps meter squared into the board. So that would be 5 times 24 is what? Is it 120? Is that right? Into the board. Yeah, 5 times 20 is 100, 5 times 4 is 20, so it should be 120, right? That's the magnetic dipole moment of the coil. So what I want to know, though, is the torque acting on that coil. And that would be, I'm going to use a different color now for this calculation. So what is the magnetic dipole moment of the coil? It's 120, I'll just say 120 into the board, cross with the external magnetic field, which is 6 Tesla up the board. So 120 times 6 is what? 720? Let's see, 6 times 100 is 600, 6 times... Is that 720? Yeah. Okay, and the units would be what? It would be the units of the magnetic, well, it's a torque, right? So I could either use amps, meter square, Tesla, or like we learned in Physics 185, a torque is a force times a distance. I can just say Newton meters. Now, what is the direction of into cross up? So into the board, cross up. Which way is that?
Left or right?
So which one is it? Which is into? It's right. It's going to be either
Left.
to the right or to the left. So which
right.
of the two is it?
Right.
Into, the first vector is into, the second vector is up. So 4 fingers into the board, palm up. To the?
Right.
To the right.
Do it with my left hand.
That's the direction of the torque. So the torque acting on this loop is to the right. What does it mean that the torque is to the right? How does that help us understand how this loop is going to rotate, is going to spin if it's allowed, if left alone? What will happen to it? Well, if the torque vector points to the right, just put your thumb of your right hand in the direction of the torque vector, and this loop is going to spin this way, with the top coming out of the board and the bottom segment here coming into the board. In other words, the loop, which actually has 5 turns, but I'm just going to draw one here. The torque vector is that way, so the top of it is going to come out, and the bottom of it is going to go into. So it would rotate. This one coming towards you, and the bottom away from you. Get it? Like this. It will rotate like this. No? Questions?
So how do you know which direction they have flipped again? Basically coming.
So any torque vector, right? If you know the direction of a torque vector, in physics 185, let's say you have something like this. This is a wall, and this is a bar, and it's pinned over here. And suppose you hang a weight over here. What is the torque of that weight exerted by that hanging weight about, let's say, point P over here? What's the torque of it? So the torque is R cross F. R is starting at the point that you take torques about, and it has to end just the force is, has a magnitude of W, and it's down, right? The line of action of that force is like this. And so R has to be a vector that begins at point P, and the end of vector R has to be anywhere on the line of action of that force W or F. Well, the simplest thing to choose is this. So R is to the right, and the force is down. So what is the direction of a vector that points to the right, cross with a vector that points down? Which way does that point?
Towards us. Oh wait.
Oh wait, that's into the board.
Into the board? Yes? Yes? So this would be, this torque would be, whatever it is, depending on the numbers, but it would be into the board. Now, the question is, how will it rotate as a result of me knowing the direction of the torque vector? So use your right hand, put your thumb in the direction of the torque vector, and that thing will have a rotational sense this way. Now, for us, it's obvious. If I tell you, if I hang this thing over here and put a weight over there, and this bar is allowed to swing, which way will it swing? Well, it's going to swing in the clockwise sense, right? So that's obvious. But here, it isn't so obvious. But once we figure out that the direction of this torque vector is to the right, then how is it going to swing? Again, it isn't obvious because we're not used to seeing that. So it's the same rule, right? You put your thumb in the direction of the torque vector, and your 4 fingers of your right hand will determine the direction in which it would rotate, if allowed to rotate. So put your thumb of your right hand in the direction of the torque vector, and it's going to rotate this way. So if I see it from this side, this thing is going to rotate in the clockwise sense. If I see it from this side, it's going to rotate in the counterclockwise sense. Either way, this is going to come out the board, and this edge is going to go into the board. So this thing is going to rotate. Like that. Yes? Now, the other thing that I said, I think at the end of class last time, is the following. Notice that, like, if I hold this thing over here, and there's this external magnetic field, and there's a current in this coil, and I just hold it, I just force it to stay put. In fact, I can ask a question like this. If I have this coil like that with 5 turns, the current in the coil is 2 amps, this length is 4 meters, this length is 2 meters, what would have to be the torque that I have to exert so that this coil stays put? Well, then I say, what do you think?
The same in the opposite direction.
Exactly. So if, the magnetic field is exerting a torque that way, yes, with this magnitude at 720 Newton meters to the right. If I want this coil to stay put so that the sum of the torques is 0, right, then I have to come up with a torque in the opposite direction to cancel that torque. So the torque that I would have to exert would be 720 Newton meters to the left. That way, because remember, in physics 185, you learned that the sum of the torques, right, would be what's called the moment of inertia, which back then we called it capital I, which doesn't mean the same thing as current, times alpha, right? And so if I want the loop to just stay there in rotational equilibrium so that its acceleration is, so that its angular velocity is 0, 0, 0, 0, 0. That means that its angular acceleration will be 0. So I want the sum of the torques to be 0. But there is a torque exerted by the external magnetic field. And there is a torque exerted by me. That's what I asked. And the sum of those two have to be 0. So the torque that I have to exert will be the negative of the torque exerted by the external magnetic field. So that, it stays put like that. Which would be 720 Newton meters to the left. If I were to ask a question like that. Now, the other formula that is in this chapter related to coils and so on is the following. It's a formula that looks like this. And it's mu dotted with the external magnetic field. This is for the coil, and there's a minus sign. Because if I apply this torque of 720 Newton meters to the left, when the coil is like this, the coil is just going to stay there like that, and it's not going to spin. I'm not letting it spin. But if I let go of it, if I remove my torque, then the only torque is going to be this. If that's the only torque, this thing is going to have an angular acceleration. And it will spin. And we said that, which way is it going to spin? Put your thumb in the direction of the torque exerted by the magnetic field. The top is going to come out, the bottom is going to go into, and that's how it would spin. But if it's all of a sudden spinning, there is rotational kinetic energy that's showing up because it wasn't spinning in the beginning, and then it's going to be spinning. So in the beginning there was no rotational kinetic energy, and then it's spinning, so there is rotational kinetic energy. And then you may ask, where is that energy coming from? I didn't push it, I didn't kick it, I just let it go. I didn't, So the rotational kinetic energy must be coming at the expense of some stored energy in the system. So it's potential energy. But this has to do with magnetic field, so you can call this magnetic potential energy. This is another equation for potential energy that you can add to your list, to your repertoire of equations. You learned in Physics 185 about gravitational potential energy. I'll just say gravity. And actually, we discussed in Physics 185 two mathematical expressions that stand for gravitational potential energy. One of them is mgh, and the other one is minus capital G, let's say the mass of the Earth times the mass of the object divided by r, where r is the distance from the mass m to the center of the Earth. So, there are two expressions. We use mgh when the mass of the object m is it's at a small height above the ground, small height compared to the radius of the Earth. If the mass of this object, if this object is far from the surface of the Earth at some height above the surface of the Earth, some height that's comparable to the radius of the Earth, then we should use this other expression. In Physics 185, you also learn about elastic potential energy stored in a spring, and it's 1/2 kx squared. A spring that obeys Hooke's law. But we also learned at the beginning of this course about electric potential energy, and we learned about this in chapter 23. So what is the energy, what is the electrical potential energy of a point charge Q when that point charge is in an external electric potential generated by some other charge somewhere? And what we are now adding, this is the electrical potential energy, what we're now adding to this list is this. What is the potential energy, the stored energy associated with magnetic, phenomena? So it's minus mu dot with B external. So Notice that because this is an energy, you can call it magnetic, it has to be a scalar quantity. But how are you going to get a scalar quantity out of a vector, two vectors multiplied? Then they have to be multiplied via the dot product, not the cross product. Right? So torque is a vector. With torque, you gotta have a cross product over here, right? The only way to get a vector out of the multiplication of two vectors is by multiplying those two vectors using the cross product. But the only way you're gonna get a scalar quantity out of the multiplication of two vectors is by multiplying those vectors using the dot product. But then if you observe this equation over here, right? If you observe that equation, if you pay attention to it, can I erase the bottom of this here? I guess I did. Let's consider the following. What happens if there is a coil, let's say a coil like this, with current in it, and suppose this coil has been placed in an external magnetic field. And the magnetic field happens to be pointing, I'm just going to draw one line like this. This is an external magnetic field. Well, what would be the direction in this picture of the magnetic dipole moment of this, let's just call it a loop, one single turn, a coil with one turn, just a loop. What is the direction of the magnetic dipole moment of this one? It's pointing to the, which way? Right, I'm trying to draw something like this, with current coming out the top and going like this, right? So the magnetic dipole moment is this way. And notice that the angle between these two vectors is 0 degrees, so the magnetic dipole, well, the magnetic energy is minus mu dot B, which would be minus mu times B times the cosine of 0 degrees. And this is just going to be minus mu B in this case. If, on the other hand, I orient the coil so that maybe the coil is horizontal, with current going around like this, but the magnetic field is to the right, well, the direction of the magnetic dipole moment, which is perpendicular to the plane of the loop, is this way. And the angle between the magnetic dipole moment and the magnetic field vector is 90 degrees. So if you calculate the magnetic energy, it will be minus mu B. If I don't put the arrow above the letter, it means the magnitude of that vector, right? And then the cosine of 90 degrees. And that will be 0. That will be the magnetic potential energy. Now, what happens if I take the coil, and the current is like that, around the coil, it's a vertical coil, and the magnetic field that this coil is sitting in is to the right. Now, in this picture, it's kind of hard to see, but it's, I meant it to be the other way. Like this, so that mu is this way, to the left. In other words, I'm imagining a loop like this. The magnetic field is that way, but the current in this loop is this way. So I go like this, so the magnetic dipole moment is to the left, to your left. And the angle between the magnetic dipole moment and the magnetic field that the loop is sitting in is 180 degrees. So the magnetic potential energy here is minus mu dot B, which will be minus mu B cosine of 180 degrees. But the cosine of 180 degrees is minus 1, so this will be plus mu B external. So if you look at these three orientations of this current loop with current I in it, placed in this external magnetic field, which of all these orientations will correspond to the minimum energy stored in the system, the minimum potential energy, the minimum magnetic potential energy, would it be case A, case B, or case C? Which of these three energies is the lowest?
Case A.
Minus mu B, so case A. So essentially, if you have considered this problem, and there is an external magnetic field to the external magnetic field is up the page, like up the board over here, right? And there's a current like this, right? What is the direction of the magnetic dipole moment vector of this loop? Into. So the external magnetic field is up, but the magnetic dipole moment of this loop is into. So if you leave it alone, the loop wants that magnetic dipole moment vector mu to point in the same direction as the external magnetic field. It wants to be lined up with the external magnetic field like this. So if the loop is like this, with the current in the clockwise sense, and you go like this, so the area vector is into the page, that's the same as the direction of mu, the magnetic dipole moment vector. This magnetic dipole moment vector wants to point up. So now picture it. Here's the loop. And I turned out to bring it. And then the magnetic dipole, the current is in the clockwise sense, right? So like this. So the area vector, which is the same as the magnetic dipole moment vector, points this way. And it wants to point up in the same direction as the external magnetic field, so that it minimizes its potential energy. So how would it rotate if it wants this vector to point up? Then it'll just go like this. Well, this is too long. So that it lines up like this. In other words, this thing wants to rotate like this to bring its area vector or magnetic dipole moment vector parallel to the magnetic field that it's sitting in, to minimize its energy. And the decrease in that magnetic potential energy is the one that's getting converted to the rotational kinetic energy as this thing spins. Get it? No?
Wants to get like to the lowest energy state.
It's seeking its lowest. It's seeking a configuration where the potential energy is lowest. I mean, that's the reason why if I drop these keys, right? If they're, if the height is small, above the ground is small compared to the rest of the earth, then the keys, I leave them alone, and they want to minimize this energy. And so they'll try to minimize the height. So I just leave them alone and just drop so that the height is 0. If you want to think of it in terms of this equation, right? Here's the earth. Say, here's the earth. That's the radius of the earth, right? And I put the keys over here, right? So, I'm exaggerating the height of it there, but this is, you get the same message across, right? So this is R. So, this energy needs to be minimized when I leave the keys alone. But notice, it's like the keys know. There's a minus sign over here, right? So, notice, suppose I just let go of the keys. If the keys move up instead, R is getting bigger. So, forget about the minus sign for now. So, R is getting bigger. If I divide by a bigger denominator, this whole thing is going to get smaller, right? Let's say it's going to go from 5 to, it's going to get smaller, let's say, to 2. But when you include the minus sign, minus 5 is actually a smaller number than minus 2. So if the keys actually go up, the potential energy is getting bigger. Because minus 2 is actually a bigger number than minus 5. So the keys say, no, I gotta watch out about that minus sign. So what happens is that the keys, instead they want to fall to the ground so that R gets smaller. And if you divide by a smaller number, this quantity over here gets bigger. Now in that case, it might go from 2 to 5. But then because of the minus sign, it's going from minus 2 to -5, and -5 is smaller than -2. So then it goes down. Either way you look at it, the keys drop to minimize the potential energy. In this case, right, x is the distance that the spring has been stretched or compressed from its unstretched position. If you either compress or stretch a spring and then you let go, the spring wants to minimize this energy. The lowest possible energy here is 0, because 1/2 is a positive number. K is a positive number. So, x could be positive or negative, but either way you're going to square it. So it'll never be negative. So the smallest energy will be 0, and that happens when x is equal to 0. That's when the spring is unstretched, uncompressed. So you you attach something at the end of a spring and then you let go, and that end of the spring seeks that location, that configuration where x is 0, when the spring is not compressed, not stretched. So it minimizes the energy, right? And you can use arguments like that over here. I think we did when, if you have a fixed point charge over here and then you have another point charge over there some distance away, and what would happen if it went that way or this way? And, we argued using energy arguments that it would move so that its potential energy is reduced. And it's the same thing over here. It is the same idea, right? There's a configuration that will determine what the potential energy of the system is. In this case, you're going to call it magnetic potential energy, and it will always, when left alone, it always seeks that configuration where the magnetic potential energy is a minimum.
So the example, when the loop rotates until U and magnetic field is at the same, would it continue to rotate or just stay there?
No, so the magnetic field is up, right? And the loop is like this. And the way it is right now, the magnetic dipole moment, maybe I'll just do this because this is too big. Okay? So it has a magnetic dipole moment or area vector pointing that way, right? So I leave it alone, and it wants this vector to point up. So it's going to spin like this. But it's going to go like this. When it gets over here, it's going to be moving. So it'll overshoot. And it'll say, no, you passed it. So it's going to put the brakes on and then go back. And then go this way, and then maybe overshoot, and then go back, and it'll oscillate. And if there's friction in the system, it'll eventually line up and stay there. That's what happens with the spring. Attach, if you have a spring like this, right? And you have, and let's say this is x equals 0. But then you attach a mass m over here and you give it this value of x, right? So once you leave it alone with no friction, this thing starts from rest, v initially is 0, right? And then you let go, and then this thing's gonna shoot to the left. But when it gets over here, it's gonna be moving. So because of its inertia, it'll overshoot. And it'll go here, but as soon as it goes there, then, the velocity is this way, but then the spring is going to be pushing the other way, so the acceleration is going to be this way, so it's going to slow down, and then it's going to go here. Stop, and then it's going to go back, and then it's going to overshoot and go there, and it'll oscillate back and forth and back and forth. Now, if there is friction, that friction is going to dissipate the energy, and then it'll eventually find its, its way over there. So that's what's going to happen over here. It'll oscillate. And depending on what's holding this thing, there may be some friction, and so that'll eventually, until it lines up.